Hello, welcome back to my channel, While Mechanical Engineers. In my previous video, we have talked about pump performance test according to ISO 9906, and this slide and these presentations continue talking about pumps, but right now we want to talk about NPSH-R. This is very famous properties on the field application of pumps, because without knowing these properties, we will risk our pumps in operations very close or already in the range of cavitation. Cavitation is very dangerous, but before understand this NPSH required, you must understand how to test it. If not, it's very difficult to understand and to specify. Although the formula is very simple, but the most important things to understand. And again, to understand it, I think you better have to test the pump by yourself if you are the pump engineers, or if you are the client who use the pumps. You have to witness how net pressure suction head required tested on the facility. Yeah. Okay. We go to the next slide. Yeah. Actually, before talking net pressure suction head required, we have to understand the general definition of net pressure suction head. Yeah. If we go to what we call university textbook, yeah, this is a fundamental of fluid mechanics, fifth edition that I used in the past when I was a student. It said that net pressure suction head, which is the head required at the pump inlet to keep the liquid from cavitation or boiling. So this is quite interesting definition, yeah, for this NPSH. But this definition is not quite touchable to you and quite difficult to understand, yeah, if you never test the pump or you never witness the pump to when tested to NPSH. So we will talk about it later on. So after that, the definition on NPSH divide into two, yeah, NPSH available and NPSH required. NPSH available usually that refer to your installation, yeah, and required is refer to the laboratory test. To make a simple definition like this, let's say your pump operated at 100 meter cubic per hours, yeah, and then at that specific point in the test lab of a pump manufacturer, it needs around, let's say, 3-meter head at the suction. 3-meter heads at the suction when the cavitation start. Yeah, when the cavitation start. So you have to translate into your application on the field that based on the formula, yeah, at least the NPSH available on your field must be bigger, around 1.5 meters, yeah. So this according to the ISO as well. So it means your NPSH available on the field or your design installation should be 3 plus 1.5 meters. If not, that will bring you problem in the operation, and then by the time your pumps will be start to cavitate, and this cavitation very dangerous to the pumps. It looks like eating your pumps daily by daily, and then finally fail. Okay, so let's go to some physics, yeah. So we are talking about physics before we start the definition more deeper and how to test this kind of NPSH required. So first, we knew that actually water is boiling all the time, yeah. waters based on the chemical bonds, actually it can start boil. Yeah. So thermodynamically we have properties of waters and the altitude I mean. Yeah. So the higher the position from sea level, yeah, it make water easier to boil, because the higher the altitude, the lower is static pressure of our atmosphere. Yeah, because in our atmosphere there are so many gases. Yeah, nitrogens around 78%, oxygen, and etc. Actually it press everything. Yeah, it press our body, it press everything, and then we call it the pressure is actually 1 atm or 1 atmosphere or 1 bar. Yeah, so it press the water. But if you go to the higher altitude, yeah, the density of gas there is lighter compared to at the sea level. So it means the pressure will be reduced a lot, and then the water easily boil. Yeah, easily boil. That is why when you go to the mountains, you need less energy to boil waters compare when you at the sea level. Yeah. So from this point of view, we capture that static pressure is a big players. Yeah, is the big players to the waters. The lowest the static pressure, the easier the water is boil. Yeah. Yeah, when the water is boiled, of course the state of the water no more liquid, it a bit of vapor. Yeah, it a bit of a vapor. So from this graph you can see the relation of static pressure and altitude, and it affect into the waters. Yeah, water vapor properties we call it. So the next page, as you can see, this is the thermodynamic properties of waters. Yeah, there is 3 points. What we call it is here is the triple points. Yeah, here the solid state in relation with temperature and pressure. So this is this line is atmospheric pressure is 1 atmosphere or 1 bar. Yeah, so from this point of view, if you can see, the lower the pressures, yeah, the lower the pressures, the easier water to be evaporate or to become a vapor state. Okay, here is the triple points. Here is the temperatures. This is the 1 bar. Yeah, our environment's pressure. So if the pressure is lower, yeah, lower, and we take this line, yeah, take this line and this line to this line, yeah, at the temperatures of normal, yeah, 27 Celsius degree, the water will become vapor. Yeah, but if you increase the pressure at the same temperature, yeah, the water will turn here, will be a mix between liquid and vapor, but above 1 bar here, above here, it will be definitely liquid. So in relation with cavitation, as we have talked before, yeah, we have to be careful that the static pressure at the suctions, the lower you make it based on the operation, yeah, the easier water will be vapor. And then when water is vapor is really dangerous to the palm. Yeah. Okay. So what is the cavitation anyway? Cavitation is the formation of gas bubbles of flowing liquid in a region where the pressure of the liquid fall below its vapor pressure. Yeah. So it creates bubbles. Bubbles means some of the waters is no more in the liquid state, but it's already vapor state. Not all actually vapor state, yeah, but some of it already become vapor state, yeah. Some of it liquid state, and it create bubbles, yeah. So things that already becomes vapor state, it becomes small bubble, yeah, small bubbles, and then it's flowing with the waters into your pump suction together, yeah. Okay, this is the image of the bubbles, yeah, of the vapor waters or evaporated waters in the liquid waters, yeah. So what is the effect? What is the effect actually to the pumps, yeah? If this formation of bubbles flowing into the pump impellers, yeah, it creates something here, yeah, dangerous zone, yeah, when the water mix vapor with the liquid and then accumulated in this impeller area. One day it will collapse, yeah. One day it will collapse, yeah. The vapor will collapse, yeah, and they hit the impeller pumps, and the speed is very high, so jet speed, yeah, jet speed, and they hit the impeller pumps, and then finally impeller pump time by time will be damaged, yeah, whereby this heat of the pumps of the water to the pump impellers, and then finally pump impellers some part of it already removed because this heating time by times, and finally imbalance uh, and then create vibration and etc. So this is the close look of how the waters actually hit the uh, pumps impellers, yeah. So this kind of mechanism to be simplified. Okay, this damage, yeah, of the pump impellers. So how it happens, yeah. So first we have to go to this illustration, yeah. To go to this illustration, this is the waters already bubbles, yeah. Let's say a cavitation already happens, yeah, and the surrounding waters, yeah, press the bubbles, evaporated bubbles, yeah, and then evaporated bubbles, the the appearance will be changed, and this finally collapse, yeah. The water pressure from here hit the vapors, yeah. It's just like a you have a balls, yeah. You put water inside, and then you have a needles, yeah, and then you push, and then it collapse. And this collapse, the speed, micro jet speed, yeah, hit the impeller surface. So, and then by times, yeah, for sure the impeller surface will be damaged, yeah, like this impeller tips, axial impeller pumps, yeah, damaged already. And this is dangerous to the pump performance. It's no more smooth, and then also impeller no more in balance, so it create vibration, damage the bearing and etc. And finally failures of these pumps. Usually when the cavitation happens, the sound looks like a marble sound, clack, 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 like that. So I witnessed it by myself on the test rig. The sound is it's like marble, clack, 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 like that. So you can notice that cavitation is already going on without seeing the instrument. All right. So what will cavitation affect pumps? As you can see here in the slide, pump impedance unbalanced, bearing is damaged because this vibration, sub deflected, seal face damage, and pump performance likely decrease, lower capacity and lower head. In the test laboratory, usually the pressure is up and down, up and down, up and down, up and down, and create noise. Yeah. All right. So this another example of the damaged impellers because of cavitation. All right. Okay. Next. Okay, the cavitations. What is effect into the pump performance? If the pump performance, like say with the red colors, and during the cavitation, yeah, the head generated by the pumps is reduced almost 3% at the beginning stage, and then finally above that 3%, yeah, and then fell to the pumps, and then also decrease the pump efficiency. Yeah, this is the dotted lines. After during cavitation, the pump efficiency also decrease. Okay, so how to recognize it? As I said to you, noise like a falling marbles, discharge pressures fluctuating, and vibration. By using vibration spectrum analysis, you can see that the cavitation usually has typical symptoms of vibration. Yeah, like this vibration spectrum to the cavitation. Yeah, you can see there's a peak there. Usually they have a rule of thumb to see this if this spectrum is like this, and highly possible because of cavitation. So how to eliminate the cavitations? Of course, you have to increase the suction pressures. Okay, and then second, you reduce the operating flow, and the third is that's in the pump manufacturers application. They usually they have a guide fence for the high performance pump at the suction. Yeah, and then you reduce temperature fluid at the suction, but reduce temperature fluid at suction is not kind of practical situations on the field. Yeah, so the second is the more practical. So from the beginning we have to size our pump and follow this regulation and our rule of thumbs. Okay, on the fields, yeah, there are two type of pump application: the positive suction and negative suction. Due to the constraint of application on the field, usually your pumps, you design the pumps that negative suctions. Negative suctions means your reservoir below the center line of impellers, and the positive suction is above the center lines of yours of your pumps. Why they call it positive? Because if above center line, the suctions will generate more pressure. Yeah, because the difference of the height, yeah, it press the pumps because potential energy of height, yeah, press the pump, so it create more static pressure at suction compared to negative. Yeah, so it's, I think, easy to understand that let's say you put you have a reservoir 10 meters, yeah, and then at the bottom side of the 10 meters of reservoir, the pressure is higher than atmospheric pressure, because static pressure added is very simple to understand. I think let's say you have a box like this, you have here, and then according to the Bernoulli law, yeah, or static pressure law, so the pressure is here is higher than compared to here, because the mass of waters concentrated here after some of these waters, yeah, it get weak, so it press at the bottom side higher than at the top side. So that's we call it a positive, and this is a negative. So it is a picture of guide fan at suction. So now we are talking how to test it. This is very interesting. Yeah. So you test it. Follow the standard procedure as you can see here. So, yeah, run the pumps. Yeah, make it warm and etc. And then you can start the testing. So this is very critical to understand. Sorry. There are two type of cavitation, not cavitation, net pressure suction head required testing method. First method is very common, it's a throttling method, and the second method is vacuum tank method. Okay, let's go to throttling method. As you can see in this screen, I have the valve at the suction point. You know, valve, it has a very common performance chart, pressure versus flow capacity. So if you reduce the opening of the valve, yeah, it will create resistance higher, and it will drop the pressure at discharge. So in relation, usually you have a graph like this. You have a pressure here, and then you have a flow here. Yeah, and then usually is the difference of pressure between suction and discharge, or we call it delta P. Delta P is like this. Yeah, it's just like a polynomial. So it means if you let's say increase the speed of the flowing water there, it create more what we call it as resistance, and the pressure at the discharge will be lower compared to the suction. So the higher the pressure the higher the flow you flowing the waters, so it needs more, yeah, delta pressure. So from this point of view, yeah, by this method of throttling, you can play how much pressure you need after the valve, or how much pressure you want after the valve. Yeah. So for example, you start the pump at 100 meter cubic per hours. Yeah, at the 100 meter cubic per hours. First you open the suction valve fully. Yeah, fully open. Okay, it's flowing 100 meter cubic per hours. You measure it, but slowly by slowly the suction valve you close slowly by slowly. Of course the flow is almost there, it's almost same all the time. Yeah, all the time, because pumps trying to suck the water based on what it needs. Yeah, but when you close the valve slowing, you will be ended at the point where cavitation start at that flow capacity. Okay, so this is how throttling method take place. So it's very easy for us to to understand the NPSH required by throttling the valve, yeah, at the specific flow capacity. So you see, and on this graph, yeah, the arrangement is very simple by throttling, and then here's there is a motorized valve, so it's more easier for you to throttle the valve and more specific, especially when the actuator is DC. Yeah, is you can divide the valve closing or opening very small parts, and you can capture the very good data. Yeah. So how the methods, as I explained to you, yeah, in this graph, adjust the throttle valve at the suction, yeah, okay, and then when you adjust that throttle valve at the suction at the specific flow capacity, let's say 100 meter cubic per hours, is the cavitation occur? You just answer yes or no. But how to say that cavitation already occur? First, as I explained to you, sounds like a marbles and etc. Let's say that you already adjust and it meet the point of cavitation already occur. Let's say the discharge, static discharge pressure is down 30%, and the needles is moving up. Let's say for at 100 meter cubic per hours, the head is 10 meters, is 9.7, and 10 again. One is moving like a needle up and down, and then at least 3%. So that's already cavitated at your pump. So you have to record that 100 meter cubic per hours at that specific flow capacity. Cavitation occur by seeing that discharge pressure already moving up and down around 3% from its design point, moving up. So if that already happens, you have to measure the unit that you have to record. For example, you have to measure at that specific conditions how much is the static pressure at the suction. At that point, the throttling valve at the suction, of course, already meet that point, and then you measure how much the static pressure at the suction of the pump. That's very important data. Okay, this vacuum tank, we talk about this later on. Yeah. Okay. Yeah, this is me. Yeah, this is me when I was in India, witnessing the test with the guy there. Sorry. Oh my god. Back again. Where's the pointer? Sorry, yeah. This is the pen. This is me. And I work with this guy there from India. Is very warm guy, welcoming us very well, welcoming me as well, yeah, and the team of in India. Thanks to you. And then we installed the pump here. So this guy helped me to install the pump, and I witness and I record the data during the testing and etc. Yeah. Okay. So again, just to repeat, let's say at 100 meter cubic per hour, you test the pumps, and then you want to know at what point or condition that the 100 meter cubic per hours it create cavitation, and that result will call as NPSH required at that 100 meter cubic per hour for one specific pumps, for example. Yeah, different pumps, different NPSH required at 100 meter is different. Yeah, so you have to see this data sheet and ask this data sheet before you make the installation or you sizing the pumps. If not, it's dangerous to your operation cost. Yeah. All right. So go to the calculation. In this graph, as you can see, I have pump performance data sheet here. Okay, I have requirement. I have already choose. This is flow minimum, and then flow in between, and flow in 120%. You can refer to my previous slide about pump performance test according to the ISO. Yeah. So let's take one example. Let's take one example. Here, I choose at 73 meter cubic 0.35 35 meter cubic per hours. So I choose this point to know NPSH required at that point. So as you can see, the flow is tend to be constant. Roughly is about that. Yeah, 34, 74, 73, and 72 is the lowest, and etc. So is the lowest. Why lowest is I'm trying to throttling the valve. So at the point I modify again this point, this point, this point, this point, this point, this point. So I throttling the valve, yeah, at the suction, and the flow like this. So I mean at the suction I throttle the valve to meet 37.3.5 meter cubic per hours. Of course, from the beginning we opening the discharge valve, so it flow, let's say, already meet 33.35, and after that we fix that point 33.5 73.35, yeah, and then now we throttling the suction valve. So after throttling we get this data, yeah, we get this data. Now we are working about at the single this data first, and then there are remaining 4 data we have to collect. So let's say from this point of view, data first, 73.35. All right. So at that 73.35 meter cubic per hours, okay, this after throttle, uh, you have to calculate the velocity at the suction, yeah, and then we have the velocity head. Yeah, it's easy. Yeah, you can easily define this velocity head, this formula, or in this table, this one. So the velocity head is around 0.07. Okay, then you also have a velocity head at discharge, yeah, because the suction actually usually is diameter is higher than discharge, yeah. So usually the velocity at the suction here, velocity at the suctions is usually lower than the velocity at discharge, but same capacity, of course, because the normal of area is bigger at suction. Is the flow is more slower compared to the discharge. That is why the velocity head at discharge is lower than uh, uh, higher than suction. Okay. All right. So we measure that. Very easy. And then now, very interesting, suction head. So how much is the suction head? You have at that condition. Okay. There is a formula for that here. Here, yeah. So you get the data. This is the head velocity at suction, head velocity at discharge, yeah. This is a delta head velocity suction discharge, and this is the head at suction. So why minus? Yeah, why minus? Minus means that the the suction head is lower than atmospheric pressure. Yeah, yeah, lower than atmospheric pressure. So because every pump being tested is the based on the pressure difference to the atmospheric is not absolute pressure, it's a pressure difference. Yeah, so as you can see, it's logical that at suctions the static pressure is it will be lower at the flow specific flow capacity, because it will retransfer the energy from static, yeah, at the suction become flow, and the remaining becomes for static. Let's say for example the pressure of suction 1 bar, when it's flowing, when it's sucked by the pump, the this total pressure, let's say this is from negative arrangement of the pump. Yeah, as you can see in the previous slide, there are two type of pump arrangement: positive suction and negative suction. Let's say this is negative suction, so it means the energy will be transferred, one to velocity and another to the static. Okay, as you can see here, the suction pressure is become negative. Yeah, and this is the discharge head at that specific flow capacity 73.35 meter cubic per hours. And then we calculate the pump total head. Yeah, we calculate pump total head based on this formulation. Yeah, and you also calculate that based on formulation in the previous video is a pump performance test, and then you get this table. This is a head delta velocity for head of from suction and discharge. This is a head discharge, and this is a head suction, and this is the head total. Yeah, this is the head total. So you can see here the head total or discharge pressure as well is quite already changed. Yeah, so we have to choose at with specific condition that 3% reduce the head total or the discharge pressure. You can check from this data. Yeah, and then after you have that, yeah, after you have that, you make a graphs. You make a graphs according to many of this data for 1 point specific specific flow capacity 1 points. So this is the flow capacity. Yeah, and you make a graph NPSH, yeah, and then head total. As you can see the graph, yeah, the graph climbing, and then become stagnant. Okay, and this graph is the net pressure suction head meters. Yeah, this is net pressure suction head, and this is the effect to the head totals. So you make the graph. So quite interesting graph. Yeah, quite interesting graph. So here is starting point, and then finally it reaches the head a bit constant. Yeah, it's easy to understand that now is when the cavitation happen. Yeah, the discharge heads should be reduced 3%, as I explained to you. Yeah, reduce 3%, and etc. and etc. And then let's say in this area, it's quite interesting graphs. Yeah, at for 1 point of flow capacity, you make a NPSH. It's not NPSH required yet. It's NPSH in relation to head total. Okay, so let's say for one example of calculation here, we define NPSH like this. Yeah, and then this for example, you see in the graph, Based on the testing condition, the temperature of ambient 30 something blah blah blah, the water columns for thermodynamic table, the vapor pressure is 0.3 meters water column. Okay, at the time head suction is minus 3.65. Then the NPSH, net pressure suction head, at this for one data example 74.10, and this the RPM, yeah, and follow this formula, yeah, NPSH, yeah, follow that formula is 9.46. 9.46 atmospheric pressure, yeah, minus this one, yeah, the suction pressure at the time, and this is the pressure difference of the velocity, yeah, and this is the vapor pressure. Quite interesting data. You have to understand here. So why you say that I 9.46 meters minus the static pressure at the suction plus the different velocity head and the head of vapor pressure. Quite interesting, right? So we have to go to definitions of the NPSH as I explained to you before. We go to the definition. Okay, we go back quite far. I think this already. All right. All right. Okay, I think where is it? All right. So NPSH definition, which the head required at the pump inlet to keep the liquid from cavitating or boiling. All right. And the formula, as you can see in the formula, that NPSH equal to atmospheric pressures, yeah, plus, yeah, plus with the static pressure of the pump at that condition, and then plus the velocity head difference plus minus the head of vapor at that environment. So if we translate this in this formula manners, yeah, so it means I have had 9.53 meters given by environments because air is press the waters 9.53, let's say 10, yeah, to make it easier, yeah, meters, and then plus, yeah, the negative the suction pressure, but this suction pressure is negative, yeah, because it's getting lower already, and then positive plus with water's velocity of head difference, and the minus of environment's static pressure at that level point level 0.3 meters. So it means I give environment give me, and then this after that eaten by condition of the operating of the pumps. Let's say for example, when 100 meter cubic per hours of the pumps need static pressure minus 3.5 meters, yeah, and then the available pressure that given to me, or plus this, and already reduced, yeah, reduced to get that condition from 9.5, for example, and then minus 4.5, now become only 5 meter available, and this 5 meter, and I deduct again, yeah, with the at that specific point the environment vapor pressure at that environment is 0.4, for example. So it means the remaining available one, yeah, for 9.5 minus 4, already 5, and the minus 4 point, let's say 0.4, the remaining available static pressure at that condition is 4.6 meters. So far, I think it's not hard to understand now so far, yeah. But if you never test the pump, it's quite difficult. So I would like to repeat again. You have the pumps and you want to test, let's say, from 73.35 meter cubic per hours. So you want to know the NPSH required at that specific flow capacity. So what you do, you test the pump, you open the valve at the discharge, and then you measure the flow capacity and adjust everything to meet 73.35, and after you get that point, now you want to throttle the suction valve until you finally notice that the discharge pressure of the pumps reduce 3%. That's when the pumps start to cavitate. Alright, so you got that point. Of course, during this throttling, you get so many data. Let's say, as you can see on the screen, during that throttling you have 6 data. You record this everything, 6 data, and on what point, and you have flow capacity here, and the head of velocity suction, and etc. And then you calculate suction head and etc. and discharge head, and then we finally go to NPSH definition. So as I told you in the beginning of the definition of the NPSH, and then when it formulated, the formula is like this. Alright, so from this formula, again I would like to repeat. Environment give you 9.4 meters of the head. That's a environment already, yeah. And then you need to run the pump at 73 meter cubic per hours. It create suction static head minus, yeah, and then this is the vapor pressure at that laboratory according to the table of thermodynamic, yeah. You subtract that remaining head, and you get this 5.25 meters. That's what you have. Okay, and then based on the formula of like a pump performance test before, yeah, you have to using a similarity law, yeah, and then you get this, and then you you make this chart, yeah, NPSH and the head. Then interestingly, yeah, you can notice that it's like this. So it means when it drop here, yeah, 3%, that will be considered the point where cavitation start, and you have to record that point, yeah, that point you record to here, and you get here NPSH required, right? So at least one point you have at least one flow capacity, at least you have 6 point, yeah, and then you recognize the chart that head total is down, yeah, 3%. That's the point, yeah. That is the reason why you have to generate this graph, so to make it more visualized to understand. So let's say we already take this one, yeah, for example, as NPSH required. So quite interesting. So let's say NPSH required there is a 5.25 meters. So what is the meaning? What is the meaning of this? The meaning now is very simple. So after I run the pump on the test lab in the pump manufacturer, I got that at 73.3 meter cubic per hour, NPSH required 5.25 meters. This already including when the need for the cavitation, yeah, 4.3 meters. So it means you cannot lower, yeah, you cannot lower your pump, your reservoir point below 5.25. If you put 5.25, yeah, the available the required head is a 5.25 meter when the start when there is a starting of cavitation at the specific point. That's a required one. But you install your pump where the where the reservoir position is exactly 5.25 meters. That's now remaining is only 0. So it means your pump will start cavitating. Why? So it's very simple. If you see this formula, this formula, yeah, this the remaining 5.25. So if you put your pump reservoir position 5.5 from the pumps, so the remaining is 0. So it means the head, the minus head, yeah, we call negative suction. You put 5, so already 0. So at least 1.5 meters. So it will be wise for this of specific condition 100 meter cubic per hours, yeah. Let's say that will 73 point something is your design point, yeah. So it will be wise for you to put the pumps not 5.25 meters from ground level to the bottoms, but let's say 2 meters. So that's the most important things how to understand this, yeah. NPSH requires, and then 8 NPSH available. So when you put 2 meters, that will be called NPSH available, and you see your pump's performance chart. Okay, I have from 73 meter cubic per hours, I have NPSH required is 5.25 meters. So now how much NPSH available I have to make there, yeah. So you have to compare this data, yeah, So usually NPSS is a rule of thumb. NPSS availables, yeah, it should be bigger than NPSS required, if not dangerous. Yeah, so it means let's say you put NPSS for this case, you put NPSS availables around let's say um, 6 meters. Yeah, you put 6 meter, and then because it required 5.25 meters. Yeah, so you put higher than required, let's say 1.5 from 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 that point. Yeah, so so far I think we have to think in this simple way. So far I believe you already understood how to test the NPSH, and then how to translate it, because NPSH required, yeah, when the pumps head discharge getting 3% lower, and then so that will be the cavitation capture as occur, and then you calculate the NPSH required at that specific point, and then you have NPSS available on the field. Yeah, just for simple calculation, usually NPSS available on the field is just simply they set the distance of the pumps to the bottom side of the reservoir. Okay, and then you compare NPSS available how much, yeah, NPSS require how much. So NPSS available, for example, let's say 3 meters, 3 meters your reservoir to the pumps. Yeah, 3 meter distance reservoir below the pumps, and the simplified formulation, let environment give you 9.46 meters head, and then 3 meters different you make, so you have remaining ones is 6 meters. And then when the 6 meter is to simplify formula, 6 meters, we will call it NPSS available, and then you need 5.25 meters required. So available is still bigger than required, still okay. Yeah, still okay. But again, maybe NPSS available here is same formula actually, like this, but without boiling evaporating pressure. Yeah, same formula with this. Yeah, but usually to simplify it, NPSS available, you just make head of environment, yeah, minus the distance between your pumps and the reservoir. Of course there is a losses there, flow losses, how many, the higher the flow, you calculate using Modi chart at the piping, how much the losses and etc. But just to simplify, you just put it. So now it's very easy already. You test NPSS required, and then you compare with NPSS available. So definition of NPSS required, after you watch this video, you know that NPSS required is net pressure suction head. Yeah, net pressure suction head at suction point when the cavitation start to occur. Okay, when the cavitation start to occur, so that will be your NPSH required. Again, to repeat, NPSH required is a condition when you test the pump at specific flow capacity and cavitation start to occur. How to know to notify you start to occur? As I said, 3% of the pressure down and up at the discharge, and the marble sound, etc. You capture that. Then you compare to your design NPSH available. NPSH available is easily formulated, to make it easier and faster formulation is atmospheric pressure of given environments, let's say your plant at sea level, minus the distance of the pumps to the reservoirs. Let's say your reservoir is below your pump. Let's say the distance is 3 meters. So you have 9.46 minus 3. So you have a remaining available 6. And your pump required 2.5. Still quite good. Based on the rule of thumb, they said 0.5 meter the difference between NPSH available minus NPSH required, but usually 1.5 meter in practical. 1.5 meters. So NPSH available must be bigger than NPSH required. If not, your pump starting to cavitate. I think quite understandable right now. So we go there, and then you can see in this graph NPSH required. So this is the point where this is the point where cavitation start, and that will be recorded as NPSH required here, as I mentioned to you before. This is recorded as NPSH required. Done. You capture 1 point. Okay, now you have to test another so many point, another so many point, and let's say you already done with that so many points, and now you want to generate the NPSH required into the graphs. Say you have already 1 point start off, 2 point. This is a flow methods, flow capacity, and then this is the NPSH required. So we were here, 1 point, 73, and then we test another point, you get this, and you test another point, you get this, and you test another point, you get this. So this is quite interesting data, that NPSH required is more polynomial. So the higher your flow capacity, the more you need NPSH required. Why so? It's quite understandable that the higher the flow capacity at the suction, it means the energy given by the pressure given by environment to your 1 bar, you have to transfer this into the velocity pressure, and then static pressure. So the higher your velocity, the higher your velocity head, and it reduce the the static pressure or static head. Okay, so that is why it's climb. But the climb is not linear. The climb is a polynomial. So you have to be careful on this. So let's say your design point is here. You're operating here, and suddenly somebody open the valve, or based on you want to increase the your plant capacity into here. Be careful. Suddenly NPSH required increase a lot. So after this is for operation guys, you have to understand this. Who knows, they want to increase the capacity, be careful. But also from a design point of view, they have to inform or to make the good practice that NPSH required. Maybe they have a safety factor of 1.3, 1.4 times. So during that operation, one day someone want to increase the capacity. it will not disturb the plant performance, yeah, especially for this crop. Yeah. So any question? Okay, we haven't talked about the uh, NPSH required testing based on the vacuum tank, but the method is the object is the same. The vacuum tank, yeah, the vacuum tank usually for the small pumps, let's say 10 meter cubic per hour. This vacuum tank, yeah, this for only for small pump. The vacuum tank working principle is simple, yeah. The water flowing into the tank there, yeah, into the tank there, but the air at that tank sucked by the vacuum pump. So if the air suck there, yeah, it means that the pressure there also reduced, yeah. So in other words, in other methods you are playing with the throttling valve, but here in the vacuum tank you are playing with the vacuum pump. So you operate the vacuum pump to meet until the cavitations occur, that I explained to you. 3% of the head discharge change, yeah, that will be started as a cavitation occur. So that's only the difference. But vacuum tank is not practical for the big pump, because for the bigger the pump flow capacity, the bigger you do the tank. So it's not economical to build a big vacuum tank. Here is for example in the photograph, this vacuum tank is only for 5 to 10 meter cubic per hours of flow capacity. Our example is 73 something flow. Is almost 10 times, yeah. So if you insist to test the pump is 73 meter cubic per hours in the vacuum tank, maybe your vacuum tanks will be the size of the house, yeah, big house. It's not economical. It's only for the small pump. But the vacuum tank is the most good things of the vacuum tank is the pressure there is more stable. The static pressure there is more stable and fast to react. Yeah, you just adjust the speed of the vacuum pump, and you can easily get with the situation when this cavitation occur. So from that point of view, just to summarize again, that it's not so easy to understand NPSH required uh, unless you witness the test on the manufacturer test rig, yeah. But using this presentation, I believe it's easy for you to understand that NPSH required is actually to find the net pressure suction at head suctions, net pressure suction head when the cavitation start to begin. So at different flow capacity, of course, NPSH required is different, and the relation between them, as I've shown you in the chart, yeah, here, NPSH required will be increased polynomial if you increase your flow capacity, and the NPSH available on your design or on the field installation is generally, to make it easier, is the head of environment pressure 9.46 minus the distance between your pumps to the bottom of the reservoir. Let's say 9.46 minus 3, and you have remaining 64.6. And for example, NPSH requires your dataset pump at that specific flow capacity 5.25. You still save, but be careful. One day someone opening the valve, and then NPSH required now is higher than NPSH available. That the nightmare starting in your palms installation. So I believe that's quite already I explained. If you have any questions for this case, please write down below. And if you want this material, yeah, and you want to maybe to correct me in some point that I'm wrong in explanation, just send me the emails. And then if you think that this presentation important and interesting, please like and share. Thank you very much. Bye bye.